All right. Hi, everybody. This is Matt from ceramicmaterialsworkshop.com, and we are here today to talk with you about glaze application, or at least the technical side of glaze application, what you need to know to make the most out of your glaze application. Now, there's a lot of different ways to apply glazes. Depending on how you work and what your experience level is, that you're going to try different methods. And in general, those fall into three major categories. There's the dip, brushing, or spraying. And they're all doing exactly the same thing. They're putting a thin coat of minerals on the surface of our clay that we eventually fire, and when we fire, it turns into glaze. And let's be clear, all glazes are made of the same thing, which is a collection of natural minerals, some refined minerals, and some manufactured minerals. But commercial glazes, all the different types of glazes that you've seen out there, they're all made of basically the same thing. Make it at home, buy it from the store, it's the same thing, they're just processing it before you get to it. Now, many of us think of glazes in different ways. Some of us have only ever gotten a pint jar of commercial glaze, and that's fine. There's no judgment there. We don't all have the luxury of making our own glazes, although I will say making your own glazes is very easy and everybody can do it. You just need to build up the confidence to do it and get some materials and equipment. I do have to add one little side note. This jar from a commercial glaze is one of my favorite details that they added in the little note here, kiln required. Love that. But whether or not you're buying it commercially or you're mixing up a bucket on your own, it's still the same thing inside. So what is a glaze? Of course, a glaze is a very thin coating of glass on the surface of a piece of pottery. Of course, I'm saying pottery. I am not trying to leave out the sculptors out there. I personally am a slip cast sculptor in my own studio, but saying pot is easier. Now, it is a thin coat, and in fact, these images are some really cool examples of what a glaze actually looks like. These are cross sections of some pottery glazes in a scanning electron microscope. These are taken by my friend Dave Finklenberg. The little orange circles show the relative diameter of a human hair. Most glaze applications are somewhere between 50 and 500 microns in diameter, and a human hair is about 100 depending on your hair. And in comparison, the average thickness of a pot is about 7,000 microns thick, which means a glaze coating is roughly 1/25th the thickness of that pot. But this is when it's fired. Of course, the fired glaze comes from our raw materials. Almost all glazes are made from a collection of, like I said, naturally occurring or sometimes processed raw minerals. But most of the time they are naturally occurring straight out of the earth. And this is a collection of minerals that would all work together to make a nice blue glaze at cone 10. We've got nepheline syenite, which is a feldspar, technically a feldspathoid, but it's providing one of our fluxes. Whiting, calcium carbon is providing another. EPK is an American kaolin. If you've ever wondered, it stands for Edgar's plastic kaolin because it comes from Edgar, Florida, and kaolin is the name of the mineral. And then flint or silica. In the States, we call it flint pretty interchangeably. Some international locations, they don't use that term, but in the States, when we say flint, we mean fine powdered silica, about 325 mesh. And then last in this grouping is, of course, we've got cobalt carbonate, which is a colorant. It's just there to add color to our glazes in most cases. Now, as I said, most of these ingredients are just naturally occurring minerals. This is a picture of a kaolin deposit in Venezuela. And kaolin is the base mineral that makes up all of our clay bodies, but also goes in pretty much every glaze. And in its natural state, it looks like a very white rock. Nothing particularly special about it. But the rock itself is not the interesting thing, because what we care about in our glazes and our clay bodies of what is going on at the microscopic and the chemical level, because that's really where our glazes and clays perform chemically. This is an interesting picture, or pair of pictures. These are what silica, flint, and a feldspar look like in the scanning electron microscope. So again, we've got down here that diameter of a human hair, quite small. And these are rocks, though. That is the important detail. That even though the material is very fine and we cannot see them as rocks with our naked eye, when we see them at scale, they are, in fact, just tiny, tiny rocks. Now, even when we rub these between our fingers, they feel like a plain old powder. You can't tell that they are rocks. That's because our fingers are terrible at judging things that are very, very small for scale. But in fact, on their actual scale, they are just tiny rocks. We have taken those large rocks and ground them down into a fine powder. Now, these materials themselves look very, very fine on their own, but they are nothing compared to kaolin. Kaolin, of course, being that base mineral that makes up clay. This is kaolin. This is Grollig kaolin, which is a kaolin out of the UK. In the UK, they'll often call it just China clay, but in the States, we go by a brand name of Grollig. And here's the thing, although I have shown this picture the size of the other ones, this black square here is actually the size of these materials. This is 1/50th the scale of these larger materials, because kaolin on a mineralogical scale is incredibly fine and smooth. So all of these materials, when we get down to it, are tiny, tiny little rocks. And what we're using them for is their chemistry. Now, to make a glaze, of course, you need a formula. And as I said, commercial glazes are no different. They're really using very similar formulas to those that are out in the world. But if you were going to make your own glaze, this would be what one looks like. This is a very common glaze formula for a basic cone 10 glaze called 4-3-2-1. It's 4 ingredients. When you add them all up together, they equal 100 plus the colorant. It's technically 101, which is another topic for another day. But in this case, they equal 100. Those are the nepheline cyanide, which represents our feldspar, the whiting, also known as calcium carbonate, which represents our alkaline earth flux. We've got clay, kaolin, we've got flint, silica, and all of those together add together to equal 100, and then our colorants go on top of them. You weigh out your materials, you mix them together, and then that's your glaze. That's about it. But what we really want to talk about is the application. You see, when we apply glaze to a pot, we sort of see it as a liquid that becomes a slightly dry powder when we put it on the surface of our pot, but that's not actually giving us an accurate perspective on what is going on inside of our glaze, because a glaze applied to the surface of a pot is actually millions and millions and millions of tiny particles all packed together like this. You've got your clay particles and your feldspar particles and your silica particles and your whiting particles all packed there on the surface, and that's pretty much it, okay? But the more important detail is what happens when we melt them. These images here are some of the coolest images you will ever see, and these come from my friend Tom Lamb. Tom was a student back in my research days at Alfred University, and Tom now works in scanning electron microscopy at the Smithsonian. So you know he is legit, but these are absolutely beautiful. This is a glaze melting, okay? And this will absolutely blow your mind. What we see here is the actual process of a glaze melting, because at Alfred University, they have got a kiln with an electron microscope in it, so we can actually see particles melt. And this is a beautiful transition. It is in Celsius. I'm sorry, Celsius is the language of the sciences, but you can figure it out in Fahrenheit. But at 800 degrees Celsius, we are starting, and that's pretty hot. That's already about cone almost 020. And what we can see is we've got large chunks of feldspar and quartz, and then there are lots of little clay particles. That's what all this ghosty, hazy stuff is all of those clay particles. We go up to 1050. This is about cone 05, and what we can see is that the glaze is barely melting. Not much is happening. We go up to 1,000, same thing. 1075, same thing. It's not until we get all the way up into about 1200 C and 1250, this is about cone 4 to cone 6, that things actually start melting. We can see the glaze particles or the clay particles coming together and the glaze now starting to form a melting homogeneous mass. Okay, then at 1270, 1300, and then at 1330, right behind me, as I move, it just looks smooth because that is the glaze completely melted. And under the SEM, a glaze doesn't look like anything. There's nothing to see in the microscope. But this is a really important detail because it does show that nothing really happens in our glaze until the last 100 degrees C of the firing, about 1230 to 1330 in this case. Nothing's really happening up to that point. And that's a really important detail if you go and look at your cone chart, but that's another talk for another day. But back to application. When we apply a glaze, we really need to think about the process of what goes on during that application, okay? Because we are relying on a really important property that we're often not paying attention to, and that is capillary suction. And capillary suction is suction that is created inside our clay bodies that extracts water from the glaze. And this is why glaze application tends to dry so quickly. So let's draw out a cartoon of a glaze being applied. So we dip our pot in glaze, and then what happens is that the clay body at the bottom starts sucking in water through this capillary suction. And as it draws water in, it's pulling glaze particles to the surface. We then remove the pot from the glaze, and then the particles stay behind, but the water continues to get sucked into the clay body until the glaze is completely dry. That's why if you've used a dipping glaze, they tend to dry within seconds, almost seeming instantly dry but by the time you pull it out, or very soon thereafter. And that's because the water didn't evaporate. It went into the bisqueware. Okay. Now, this is really, really important because now the water is there inside that bisque and not in the glaze, but that doesn't mean we don't have to get the water out. Of course, the water does dry eventually by becoming water vapor and rising back out to the surface and eventually going out to the atmosphere. But this is a process that happens rather quickly and you just never see it happen. Usually it'll happen soon inside the firing as soon as you turn on the kiln or if you let it sit around for a while before you put it in the kiln. But it is the capillary suction that is important because that is what is drawing the particles to the surface. This is why re-glazing a pot that's already been fired to temperature is so difficult because there is no capillary suction. We have melted the glass and glass doesn't have any suction, but open bisqueware does. When you're trying to reapply glaze to an already fired surface, you are hoping that the water evaporates, but it really doesn't, which is why it just tends to run off, and that the solution for making a glaze stick to an already fired piece is heat that piece up. The heated piece then becomes a radiator, which forces the water to evaporate, and then you can get some reapplication. But that is a dip application when you are going to dip in and rely on capillary suction. There is also a spray application, and spraying tends to be the most rare in the arts, although it is commonly used in industry. It's used quite a lot. In a spray, we're taking the same liquid glaze, but then it's atomizing the particles. So it's turning the particles into little granules of individual glaze, little spheres, and those are thrown at the surface through the sprayer, and then they stick and give a quite good application because you get a lot of diversity of particle sizes. Spraying is wonderful, but there's not a ton to be said about it. The common method for many people, especially as they're starting out, is a brush. Of course, if you're working with a commercial glaze, you're generally buying it in a pint volume, which is not a lot of glaze, and you tend to brush it on. Brushing glazes are no different chemically than a dipping glaze or a glaze you make yourself. The difference with a brushing glaze is usually the glaze company will be adding suspension agents and brushing medium. This is to keep the glaze floating in the water as it sits around on the shelf for months and months or years. And the other is the brushing medium, and this is intended on keeping the bisqueware from having capillary suction. Because if you've ever tried to brush on a dipping glaze, what happens is that the brush just dries up right away. The water gets sucked into the bisqueware, and then it becomes hard to push around. Most commercial glazes will add in a medium that keeps the water from being absorbed in the bisque very quickly so that you can push it around and try to level your application. But as I said, the actual formulas and chemistries aren't all that special. But we do have to talk about that bisqueware because the bisqueware is incredibly important. Of course, the great question that we always have to ask is, why do we bisque? Now, you will find a multitude of reasons, but there is one simple one, which is explosions. We do not want to find out that our work has exploded after a glaze firing and all over the other work in the kiln. Now, yes, bisquing does make the work more durable for the glazing process, and it does remove some volatile compounds from the clay, like chemically bound water and carbon dioxide and some sulfur compounds. And that is true. But that's actually not all that important because of when our glazes melt. As we saw in the earlier side, most of our glazes don't melt until the last 100 degrees C of the firing. All of that stuff that you've been told that you have to get rid of and you have to get a clean bisque, it's actually kind of nonsense. Because our glazes aren't melting, there is still an open network for any of those materials to get out of our glaze. There's a lot of myth and rumor about different reasons to bisque and to do this and to do that. And it's a lot of correlation does not equal causation, but that's another conversation for another time. Of course, the last reason why we bisque is that we actually want to kill the work. We want it to break so we don't waste time glazing. One not uncommon trick in industry is that they will actually bisque to cone 10 and then glaze to cone 04. They do this because they don't want to waste the space in the kiln firing finished work that they know is going to die later. They want everything that comes out of the glaze firing to be successful. So they would rather kill it early than to waste time in their precious firing with their final work. It does make it harder to apply, but they have tricks for that. And similarly for us, we hope that the work will die in the bisque. We don't always see it. Quite often, the glaze firing gets the blame of, oh, my work broke. Oh, it must have been something that the studio tech did or something in the kiln, when realistically, nah, it just didn't have a chance to die yet. And that's just the reason. But of course, the real reason why we bisque is explosions. We want to try to get explosions out of the way. Now, we do have to lay this out, and this may be controversial, but your work did not explode because of air pockets. Full stop. I repeat, your work did not die because of air pockets. Your work died because of moisture. Now, you may say, oh, that sat on my shelf for 6 months before I fired it and it exploded. Yup, still moisture. Air is not a problem. You see, steam is a huge problem. When you build a sculpture and your teacher told you to put a little pinprick in there, that wasn't to let air out. It was to let steam out, because if steam builds pressure, then it becomes explosive. Steam runs the world. Most electricity in this world is still generated through steam. Natural gas power plants burn natural gas to boil water to make steam. Nuclear power plants are literally just giant tea kettles. They are using nuclear power to make a huge amount of heat to turn water into steam to turn turbines. Water is the reason why your work exploded. Air can get out. Steam builds pressure and it can't. Now, in your bisque, of course, that steam, water is going to turn to steam at 212 degrees Fahrenheit or 100 degrees Celsius. And that is a smart thing to do to your bisque, to add in a dry cycle there to prevent explosions. But we are bisquing to have work explode. If you are once firing glazed work, let's say, and the steam hasn't gotten out and you get an explosion, what's going to happen? you are going to get shrapnel of glazed work all over everything. All over the pots, all over the shells, all over your elements, all over the walls, all over the furniture, all over everything. And you won't know that that explosion happened until after your glaze firing is done, because most explosions are actually pretty quiet. It's not a boom, it's a poof. So you really need to be aware, and that's why we bisque. We want to make sure we don't get explosions during a glaze firing, because that is really bad. Now, as to Bisque temperature, I like cone 08. Now, I'm going to tell you, many people are going to come and argue in the comments section of this video, and I am not going to read those comments. I am not here for an argument about Bisque temperature. You do you. I like cone 08, and I'm going to show you why I like cone 08. I am an advocate of a lower temperature bisque. Yes, I have heard all of the arguments, and no, they don't influence me. My background is to study the science of ceramics in an artist perspective. I get it. But I also think that, again, the correlation causation relationship of why most people say a higher bisque is misappropriated, and a lower bisque has a ton of advantages. At the end of the day, the actual temperature is not as important, but what is important to have a consistent bisque temperature and to have a consistent bisque temperature for different clay bodies. Now, I live in the luxury of I just use one clay body, but what we will talk about is that if you start switching clay bodies and switching bisque temperatures, you're going to have problems. You need consistency to get a consistency of application. And what do I mean by that? Well, let's look at a glaze. Here is a glaze called DDM222, and you can find it on Glaze. Its formula is right here. But what we have on the screen is 4 different test tiles. And the thing is, these 4 test tiles are exactly the same glaze in exactly the same firing. The only difference is how long I applied the glaze onto the tile. This was all done with dip, but we've got in the upper left-hand corner a very quick dip, then a 2-second dip, a 4-second dip, and a 6-second dip. And you can see the effect of this glaze changes radically as you get a thicker and thicker application. Now, we can talk about why you get that at another time, but some glazes need a particular thickness to get a particular quality of glaze. And this phase-separated oil spot is no difference. You have to get it just right on the thickness. It lives in a Goldilocks zone. But a couple of things to know is that I also mix this glaze with 60 milliliters of water in a 100-gram dry batch. And this is the first thing that I would advocate to you. Measure your water. I firmly believe that we should all be listing water when we are listing glaze formulas, because water content dictates how a glaze will perform. And what do I mean by that? Well, let's look at this. You see, here are 8 glazes, except once again, they are all the same glaze. And what we have here, though, are 2 different variations on the glaze. This particular is the same glaze with 50 grams of water. And what we have is a 2-second dip, a 4-second, 6-second, and 8-second of the same DDM222 glaze. But what we have is the difference is the top row, the clay was bisque to cone 08, and on the bottom row, the clay was bisque to cone 04. Well, isn't that interesting? These are all exactly the same glaze. Why do we have such variation based purely on bisque temperature? Well, we have to go back to capillary suction. You see, at cone 08, my body has lower absorption, which means it absorbs more water. Higher absorption, which means my clay body absorbs more water, which means it pulls more particles to the surface on application. So as the glaze gets applied for longer and longer periods of time, we are getting a thicker and thicker coat. In fact, this shows a beautiful example of something I consistently teach at glazes really run for 2 reasons. 1, they are too thick, and 2, they are overfired. Now, this is a circumstance where the glaze is too thick, and too thick actually affects the quality of this glaze. Now, I will go off on a side tangent that oftentimes people will say, oh, why did my glaze run when I layered these 2 glazes? You'll often find everybody online jumping in and saying, oh, you've got some magic eutectic reaction where all of a sudden you've created a new lower temperature. No, you didn't. What happened is you just put on two really thick coats of glaze and you didn't really think about it because we have sort of a distorted view of how thick a glaze application really is. Okay, and it's very easy to put on two really thick coats, especially when you're layering them. So just be aware of that. So in this case, we can see at cone 08, we got a very thick coating, but at cone 04, suddenly the 2-second dip doesn't have that same effect. In fact, it's not until we get to the 8-second dip where the glaze begins to look the same. Well, that is because there is lower absorption in my clay at cone 04. Now, once the glaze gets thick enough with the 8-second dip, the glaze starts to look the same as the 2-second dip at 08. But this is why having a consistent Bisque temperature is so important. If you Bisque to cone 08 one day and cone 06 the next day and cone 04 the day after that, your application qualities are going to be completely and utterly different. You need to stay consistent. You can recreate this glaze at a cone 04 Bisque, but you need 4 times the length of application to get it just right, to get the number of particles you need to make the glaze work. If you're bisquing hotter, it's going to be a problem. But the Bisque temperature is not the only complication. You see, this is all the same glaze, but now I've mixed it with different water contents, but use the same application time. So these are all with the 8-second dip with a cone 08 Bisque. But this tile is mixed with 50 grams of water. This is 60, 70, 80, 90, and 100. And amazingly enough, now the 100 grams of water at 8 seconds at a cone 08 Bisque looks like our previous sample at 50 grams of water with a 2-second dip, right? With an 04 Bisque, because the application doesn't change. You'll often hear people say, oh, well, the glaze is changing because of the application. No, you're literally just not getting enough glaze particles. In this case, the water content is high, so while the Bisque is absorbing water, it doesn't have as many glaze particles that are coming with it, so the glaze application ends up thin. Again, this is really why water content should be part of your formula. You should always be mixing with a consistent water content along with a consistent Bisque temperature. These types of changes, although they may seem like minor, will give you huge variations in the quality of glaze application that you get. This is the same test, though, with a cone 04 Bisque. And again, that we can see with the 8-second dip, it's fine at 50 and it's okay at 60 grams of water, but at 70, 80, 90, and 100, we lose the effect. The glaze application is too thin. Why is that? Well, at cone 04, my clay body has 16.86% absorption, but in the previous slide, we saw that at cone 08, my clay body has almost 20% absorption. Now, you may say 3% absorption, who cares? But the glazes care. Again, this is cone 08, this is cone 04. Same glazes, just different Bisque temperatures and different water contents. It makes a huge difference. Now, the other thing to understand is don't assume that all clays are going to benefit from the same Bisque temperature. This is a firing curve from some B mix that was sent to me by my friend Stacy Morgan, and I ran its firing profile to check its absorption. The interesting thing is that on this B mix at cone 06, the clay body had 15% absorption, and at cone 04, it had 11% absorption. Now, once again, my clay body that I'm working with at cone 08 has 20 and at cone 04 has 17. So even two different clay bodies Bisque to the same temperature are going to have radically different applications. Don't assume that you're going to get the same application with a 3-second dip on your B mix that you are going to get on a 3-second dip on your porcelain. You need to cater the application to each and every clay body and each and every Bisque temperature. There is no one single answer. You really need to watch all of those details. It's going to make a huge deal. And again, that's what we see when we look at these variations in the thickness. that with higher Bisque temperatures, with higher water contents, we get different absorptions and different amounts of particles in the glaze. There is something else, though, that we need to be aware of when we're talking about water content, which is a few metrics that we can use to keep our water content consistent. There is a notion out there that you may have heard of called specific gravity. Specific gravity is a reflection on how much material and water together are inside a glaze. And it's a pretty simple test to use, and it's a really good one to keep your glazes consistent as you use them. This picture is an example of me measuring specific gravity. I have used a syringe, and I have extracted 50 milliliters of glaze. I then weighed that syringe and found out how much material was in it. That was 86.09 grams. This is, of course, had been tared, so the syringe is not in the measurement. To measure the specific gravity, I divided the 86.09 grams by 50 milliliters for a specific gravity of 1.72. Now, what does that mean? It doesn't actually mean a heck of a lot without a little bit of context. And of course, that context is that the specific gravity of water is 1. And so the thicker the glaze gets, the more particulate is in there, the higher the specific gravity goes, and the more material there is in the suspension. Now, a lot of people will push specific gravity as a panacea, as the answer to understanding all glazes. Much like the fact that there's not one Bisque temperature and one absorption level, there's not one specific gravity for every glaze. Some glazes are great at a specific gravity of 1.7, some are great at a specific gravity of 1.5. It all depends on the materials in the glaze and the way that you use the glaze. And on top of it, specific gravity can lie to you. Again, you have to be very careful because a lot of people will go around saying, oh, specific gravity, that's what you need to know. That's how you keep a glaze consistent. And it's not. You see, here is that same glaze with a specific gravity and its weight is 86.09. Here is a second glaze whose specific gravity is essentially the same, right? Two different glazes with relatively the same specific gravities. But here's the problem. This is a video of those two glazes pouring in slow motion. Now you can see the glaze on the right is very, very thick, but the glaze on the left is very thin like water. But these are the two glazes I just showed you with exactly the same specific gravity. But the problem is I have manipulated the viscosity of these glazes. And viscosity is just as important as specific gravity. Viscosity is how does a glaze flow, because it doesn't just matter how much the water to particles are influencing the glaze. It also matters how that glaze flows. And that is incredibly important because that's going to affect, again, our dipping, our dip times, our bisque quality will be affected by viscosity, okay? And viscosity is a pretty simple measurement that most people are ignoring, and we really advocate that people do. Viscosity is measured with a Zahn cup or a Ford cup, and this is an example of some Zahn cups at work. These are 5 different Zahn cups that we have, and each Zahn cup has a different diameter hole, as you can see down at the bottom. They're labeled from number 1 to number 5, and they all work the same way. Basically, when the hole is small, the water drains very, very slowly. When the hole is big, it drains very, very quickly. Now, you can use any of these. The metric that you use is very simple. It is literally just start a stopwatch when it begins to drain. So we're going to fill up the water here, and then we're going to drain and just do a count. 1, 1,000, 2, 1,000, 3, 1,000, 4, 1,000, 5, 1,000. The first is done. So on and so forth. The thing is, we like the number 4 Zahn cup, which is the one that's going to stop next here in the video, because it takes more time to drain. Most places will sell a number 2 Zahn cup or Ford cup, and that's not great because it drains very quickly, so it's harder to get an accurate measurement. So we tend to like a number 4. You can buy these on Amazon. Just be careful buying these from auto supply stores. They're going to tend to sell the number 2 because most of the time Zahn cups are sold for oil in cars and mechanics and the like. So just be careful and aim for that number 4 if you can get it. But that number will help you maintain your viscosity. So you mix up a new batch of glaze and the Zahn cup is draining in 20 seconds instead of your normal 30, and you can go, oh, this glaze is really fluid, something must be off. One thing to watch out for of things being off is that some glazes need time to age. About 3 days is what you want to look for, and then they will shift their viscosity in that time. But if you combine a viscosity measurement with specific gravity, with measured water, you should have pretty good control over your glaze. So, understanding your glaze application really does come down to understanding your material, both your clay and your glaze. And we really want to emphasize going forward that you should consider everything that goes into your glaze to get a consistent application. The method of the application, whether it's dip, spray, or brush, or something else, the kind of clay that you're using, the Bisque temperature that you work at, the fact that each and every glaze is going to be different, the measured water content, the specific gravity, and the viscosity all come together to help you understand your glaze and make it better. Well, that's it for now. Thank you so much for spending this time watching. If you want to learn more, join us at ceramicmaterialsworkshop.com. We have full online self-guided workshops or full courses that we have to teach you about how your glazes really work to allow you to master your glazes and end post-firing depression. They will change your studio forever, and we hope to see you over at ceramicmaterialsworkshop.com. Thanks. Bye.